Assalamu alaikum. Welcome, dear students, to a new unit in our school year, Unit 4 Mechanics, with the first chapter, Chapter 14, Description of Motion, Part 1. By the end of this chapter, you will be able to explain the relativity of rest and motion, characterize the position vector, distinguish between average and instantaneous speed, describe the principle of functioning of the air table, determine the value of the instantaneous speed, and distinguish between average and instantaneous acceleration. In our video, we are interested in the first three objectives. Let's start by introducing our new unit. The world around us is full of moving bodies. Classical mechanics is a branch of physics which studied the motion of bodies under the action of forces and helps to establish the laws which govern this motion. In this year, we are interested in studying two main branches of mechanics: kinematics, which study the properties of motion, its position, velocity, acceleration, etc., without relating it to its causes. These objectives will be studied in Chapter 14 and 15. The other branch is dynamics, which is concerned with the study of forces and their effects on motion. These objectives will be studied in Chapter 16 and 17. Let's start now with our first objective. While sitting on your chair watching the video right now, you are at rest relative to the chair. Yet, you are moving with a speed of 30 km per hour around the sun. Thus, motion is relative. Actually, an object is said to be in motion when it changes its position with time relative to the chosen reference. Then, if there is a change in position relative to the reference, then the object is described to be in motion with respect to that reference. Whereas, if there is no change in position relative to the chosen reference, then the object is described to be at rest with respect to that reference. In our previous example, the reference was the chair, and the boy was described to be at rest relative to that chair, since its position didn't change with respect to the chair. Whereas, when the reference was considered to be the sun, the boy was in motion relative to the sun, since its position changes with respect to the sun. Any moving object follows a certain trajectory. The trajectory is the set of positions occupied by the object during its motion. Followed path. Trajectory could be either a straight line where the motion is rectilinear motion, or a curved line where the motion is a curvilinear motion, or a circled line where the motion is a circular motion. In this year, we are only interested in studying rectilinear motion where the trajectory is a straight line. Going back to the definition of motion, let's have a stop on the terms position and time and how to deal with each one of them. Consider ball A at 3 meters from a hole, while ball B is at 2 meters from that hole. Distance expresses position. But is it enough? Now consider another ball C at 2 meters from the same hole. Can we say that B and C have the same position relative to that hole? Of course not. To describe the position of an object relative to a reference, we need to talk about both distance and direction. Thus, we need to describe the position as a vector. To do so, we will use a space frame of reference, which is a system to which all the positions can be determined. It is formed of an origin, the reference, in our case the hole, and set of axes, one axis in rectilinear motion. Each axis is characterized by a unit vector, which determines the positive direction of the axis. Moreover, the length of the unit vector defines one on the axis. To define the position vector, consider a particle m moving along the x-axis. The position of m at an instant t can be represented by the vector r vector equal to om vector equal to xi vector, where x is the abscissa of m. This is the position vector of m at an instant t. This is the abscissa of m at that instant. The characteristics of the position vector are as follows: the origin O, the line of action, which is the line holding the vector OM, in our case the x-axis, the direction, which is from point O, the origin, to M, and the magnitude, which is the distance OM or the norm of the vector OM, which is calculated at the absolute value of the difference in the abscissas of M and O. Let's now write the expressions of the position vectors of balls A, B, and C and schematize them. The position vector of A is written as RA equal to OA vector is equal to the abscissa of A relative to the origin O, which is equal to 3I. And here is the representation of RA. Similarly, RB is equal to 2I, and here is the representation of RB. And finally, the position vector of ball C is written as minus 2I, and here is the representation of RC. Note that the negative sign indicates that the position vector of C is directed in a direction opposite to the positive chosen direction of the axis. Another reference which helps us in describing the motion of an object is the time reference. The time reference allows us to determine the instant or duration of an event. The instant t at which an event takes place is determined relative to a certain original initial time, usually t0 equal to 0. For example, when we say we are in 2021, then the initial time is considered the Christmas. While when we say we are in 1442, then the initial time is considered the migration of Prophet Muhammad. In experiments, the best initial time is the first moment any experiment starts. Time is expressed either as an instant, t0, t1, t2, where t0 is the original time or the instant at which we start timing. It is measured using a watch. Or it is expressed as a duration, which is a time interval between two instants, where delta t is equal to t final minus t initial, or t2 minus t1, etc. The instruments mainly used to measure the duration of time are the stopwatch or chronometer. Let's practice now by solving application 1. But before we start, don't forget to pause the video and try to solve the application by yourself. A particle m is in rectilinear motion along the x-axis. The figure shows the positions of m, m0, m1, m2, m3, and m4 at instants 0, 2, 4, 6, and 8 seconds respectively. Note that the duration separating two consecutive instants are constant. In the first exercise, you are asked to write the expressions of the position vectors r0, r3, r4 of the particle m at instants t0, t3, and t4 respectively. From the figure, r0 is equal to OM0 vector, which is equal to 12i, r3 is equal to 0 since the abscissa or since m3 is confounded with the origin, r4 is equal to minus 8i vector. Now let's characterize and represent the position vector of m at the instants t1 and t4. Starting with OM1 vector, the origin is O, the line of action is the line holding OM1 vector, which is the x-axis. The direction is from O to M1, and the magnitude is the distance, which is the norm of the vector OM1, which can be calculated at the absolute value of xm1 minus xo, which gives us 10 meter. In other words, it is the distance separating M1 from the origin O. This is the representation of R1 vector. Now, with respect to OM4, the origin is also O, the line of action is the line holding OM4, which is also the x-axis. The direction is from O to M4, and the magnitude is the norm of the vector OM4, which is the absolute value of xm4 minus xo, which is minus 8 minus 0, which gives us as a distance 8 meter. Also, in other words, it is the distance separating m4 from the origin. You can count it as 2, 4, 6, and 8 meter. And this is the representation of OM4 vector. Now let's indicate the instant at which the particle m reached the origin O. The particle m reached the origin at the instant t3, which is equal to 6 seconds. Now you are asked to calculate the distance covered by m between the instants t0 and t4. The distance is equal to the absolute value of the difference in the abscissas between the positions of m at the instants t0 and t4, which is equal to the absolute value of minus 8 minus 12, which is equal to 20 meter. In the last part, you are asked whether M move in the positive or negative direction, and you need to justify. M is actually moving in the negative direction. From the figure, you can notice that M is moving in a direction opposite to the positive chosen direction of the x-axis. In other words, you can say that the abscissa of M is decreasing with time. Then note here, if the abscissa is decreasing, this indicates that the particle is moving in the negative direction. Let's move to our final objective in this video. Observe the following speedometer. All of you have already seen the speedometer of your cars, which indicates the speed for you. But have you noticed the unit displayed by it? Notice the unit of the speed. It is kilometer per hour. Do you know what is the significance of this unit? Consider the following example. The speedometer indicates 165 km per hour. It means that while moving at this speed, the car covers 165 km in 1 hour. Analyzing the unit of speed, what do you expect to be its formula? The speed is measured in kilometer divided by hour. The kilometer is the unit of the distance traveled by the car, and the hour is the unit of the duration of time taken by the car to cover the distance, this distance. Then, the obtained formula is V equal D divided by delta T. Consider the following example. The Jeep covers the distance AB in 12 minutes. To calculate its speed in kilometer per hour while covering the distance AB, we start by converting the unit of time from minute into hour by dividing it by 60. Applying the formula of the speed, V equal to D divided by delta T, which is equal to 5 km divided by 0.2 hour, which gives us 25 km per hour. Note that each minute is equal to 60 seconds, each hour is equal to 60 minutes, it is equal at the same time to 3,600 seconds. Actually, the speed read by the speedometer of the Jeep doesn't indicate 25 km per hour all the time. The value indicated by the speedometer varies continuously according to the traffic state. So what does the speedometer indicate precisely? Let's see. The speed indicated by the speedometer is the speed at every specific instant. It is called the instantaneous speed. So, what does 25 km per hour represent? It is the average speed of the car, which we calculate by dividing the total distance by the total duration of time. Then, the speed could be either an average speed or an instantaneous speed. The average speed of a body in a certain duration of time is the total distance covered by this body in that interval of time divided by time. It is calculated by dividing the total distance by the total duration of time. Whereas the instantaneous speed is the speed of the object at each specific instant, and this speed is indicated by the speedometer of the car. Note that the SI unit of speed is meter per second. So, to convert from kilometer per hour into meter per second, start by converting kilometer into meter by multiplying it by 1000 and converting hour into second by multiplying it by 3600. Then, from kilometer per hour into meter per second, we divide by 3.6, and from meter per second into kilometer per hour, we multiply by 3.6. Let's practice now by solving application 2. Also, don't forget to pause the video and try to solve the application by yourself. A car leaves Tripoli at 8 a.m., arrives Beirut at 9:10 a.m., rests for 50 minutes, and then continues toward Alay and reaches it at 10:30 a.m. The average speed of the car between Tripoli and Beirut is 66 km per hour, while that between Beirut and Alay is 15 meters per second. First, you are asked to determine in hours the duration of the whole journey. To make your work easier, you can start by drawing a timeline for the different events taking place in the application. The first event is leaving Tripoli at the initial time, which is 8 a.m. and the car arrives Beirut at 9:10 a.m. Then, the duration of time between these two events is delta T1 is equal to T1 minus T0 is equal to 1 hour and 10 minutes. After that, the car will rest for 50 minutes in Beirut. Then delta T2 is 50 minutes, which means that the car will leave Beirut at T2 equal to 10 a.m. After that, the car reaches Alai at the final time, which is 10:30 a.m., which means that the duration of time between these two events is delta T3 equal to TF minus T2, which is equal to 30 minutes. Now let's answer our question. Then delta T is equal to delta T1 plus delta T2 plus delta 3, which gives us 150 minutes. But you are asked to express it in hours. Then you divide 150 by 60 to obtain 2.5 hours. In the second part, you are asked to determine in kilometer the total distance covered by the car between Tripoli and Alai. Here, it's good for you also to divide your work into 3 parts. The first part is between Tripoli and Beirut, where the average speed of the car was 66 km per hour. Then, the total distance traveled by the car in this phase or in this part is equal to the average speed multiplied by the duration of time in this part, which gives us 77 km. In the second part, which is the rest in Beirut, the car was at rest, then the distance traveled by the car is 0 km. The third part is between Beirut and Alai, where the average speed was 15 meters per second. We have the duration of time in minute and the speed in meter per second, then start by converting the duration of time into second by multiplying it by 60. Then the total distance traveled by the car in this part or in this phase is equal to 27,000 meters. Dividing it by 1,000, we obtain 27 kilometers. Now, to obtain the total distance from Tripoli to Alai, we add D1 plus D2 plus D3, which gives us 104 kilometers. And note that all the distances are calculated in kilometer. Finally, we are asked to deduce the average speed of the whole journey and express it in the SI unit. When you are asked to calculate the average speed of the whole journey from Tripoli to Alai, you need to have the total distance, which we have calculated in the previous part, and the total duration of time, which we have calculated in the first part, and divide them by each other. Then V average is equal to D divided by delta T, which is equal to 104 km divided by 2.5 hour, which gives us 41.6 km per hour. The SI unit of speed is meter per second, and from kilometer per hour into meter per second, we divide by 3.6, which gives us 11.55 meter per second. Now let's summarize the ideas of this video. In this part, we have studied kinematics, where we have noticed that motion is relative, and the trajectory is the path followed by the moving object. We've defined the space reference as a system to which all the positions are determined. Also, we've defined time reference as an instant denoted by T0, which is considered equal to 0 relative to which all other instants are determined. We've learned that the position vector determines the position of a particle m in a chosen reference, where r vector is equal to om vector is equal to xi. The characteristics of the position vector are as follows. The origin O, the line of action, which is the line holding OM, which is the x-axis, the direction from O to M, and the magnitude, which is the distance or the norm of the vector OM. Also, we have finished by talking about the way of calculating the average speed, which is dividing the total distance by the total duration of time. And don't forget that meter per second is the SI unit of speed. This is the end of part 1. Thanks for your attention.